now that we've seen the signal energy, it's time to look at signal power. Power is just energy per unit time, and so signals which have infinite energy might have finite power if the amount of energy expended per unit time is finite. So we'd like to be able to compute the power of real and complex signals. So we saw before that sinusoids have infinite energy. For example, as cosine we saw in continuous time before. And we see the same phenomenon in discrete time. So if x of n is cosine pi over 5n on the left here, then when we take the magnitude squared, we get the signal on the right here, and you can see that if you sum this up, you're going to get infinity. So here's another example of a signal which has infinite energy. However, if you note, the amount you're adding over each, like a constant unit fraction of time is sort of the same. So it's growing, the energy as I progress through the sum is growing only linearly in the with time. So mathematically, we can try to define this energy per unit time as taking larger and larger chunks of the signal, going, say, from minus t to capital T. We look at the instantaneous power and we integrate that up. So this is the total energy, this term with the integral, and then we divide by the length of the interval. So in this case, 2 times capital T, so we take 1 over 2t, and that's the total energy over the time 2t. And then we take the limit as t goes to infinity to see if we're getting kind of a constant power output. So we have the signal x of t. We can look at its magnitude x of t squared. And then we're going to look at, say, minus t to capital T, say t is 1.5. We're going to integrate up 3 of those humps. And then we're going to divide by 3. And then we could look at 5 of them and divide by 5, and so on and so forth. We can do the same thing in discrete time, but in discrete time we have to account for the signal at n equals 0. So there's a kind of a little bit of an asymmetry. So the interval from n equals minus capital N to capital N contains 2 capital N plus 1 different time steps. So that means we have to divide by 1 over 2n plus 1, and then we add up again the instantaneous power, so the total energy in the interval minus n to capital N. And we have the same picture that we saw with the continuous time signal. So we take the instantaneous power, and then we start integrating. We sum up between n equals minus 4 and 4, so that's 9. We're going to be dividing by 9 in that case. And then we keep growing, and then so on and so forth. So if x of t is periodic with period t0, then we can just look at integer multiples of t0. So we know that the signal is identical to itself every t0 seconds. So that means we can give a little proof of this. If I look at the limit as t goes to infinity of 1 over 2t, the integral of the energy between minus t and t, then I can, instead of looking at any value capital T, I can just look at multiples of t0. But in minus kt0 to kt0, I go through 2k cycles of the signal. So the instantaneous power is just 2k times the cycle in 1 power, say from 0 to t0. The total energy there. So this is just the total energy, 1 over t0 times the energy in 1 cycle. So this is the average energy per cycle is the power of a periodic signal. It's the average of the instantaneous power over 1 period. Complex periodic exponentials are a very good example of power type signals. So if we look at just e to the j omega t, then the magnitude squared is 1. So if I try to integrate that over time, I'm going to get infinity. But if I look at the period, since it's a periodic signal with period t naught, which is 2 pi over omega naught, then we're going to get from 0 to t naught of 1 dt, and we're just going to get t naught. For a sinusoid that's a cosine omega naught t, we can, again, take the square of the cosine. We're integrating over 1 period, which is 2 pi over 0 to 2 pi over omega naught, which is the same as t naught. And then we have to just do a little bit of, cosine squared and double angle formulas to get from equation 9 to equation 10. So it's a good thing to refresh your trigonometry from high school. And then when you integrate this out, you get 1. So suppose x of n is periodic with period n0. Then we can look at integer multiples of n0. again, doing the same thing we did in continuous time, we're just going to do it over, over discrete time. So we're going to take an interval of k times n0, except we're going to look at k times n0 at beyond 0 and below 0, so minus kn0 to kn0. That's going to have, again, because of that point at 0, we get a plus 1 in this denominator. So we can separate that out. We can say x of 0 squared plus 2 times k, and then we're going to have k repeats above 0 and k repeats beyond 0 of summation of x of n squared just from n equals 1 to n naught. So we take the limit here, and we can get exactly the same kind of formula. We get the average instantaneous power, so the sum of n equals 1 to capital N naught magnitude of x of n squared divided by n naught. Now, in both these continuous and discrete signals, we've been looking specifically at periodic signals, but of course you can find the energy and power of non-periodic signals too. You just have to plug it into the definition and run through the integrals. The important thing is to be able to determine when the power is going to be finite, and when the energy is going to be infinite, the power is finite, or when the energy is going to be finite. And that distinguishes between power type and energy type signals, which we'll talk about next.